We were all nervous.
I think
well, Linda got us all nervous. She said, we don't know what we think.
Yeah, but Paul was thinking out of the window. But I don't.
Hi, Bill.
I'm sorry, Bill. That's probably too much information.
You got my slide?
Yeah. Yeah, you're not.
Oh, it is?
Looking here? Gotcha. Okay, so I think then to get out of it, we just stay. And then, oh, yeah.
Okay, you pulled that.
Yeah, pretty non-controversial.
Something good about the new Acrobat, isn't it?
You think it is?
Control L. Yeah. Yeah, or I think you can do it from up here. View. But, oh, no. Yeah. Well, you can just go down here, full screen mode.
You could debate, whether the spring.
I can run up and get my pointer.
I think that I wouldn't. I don't want to just bring one.
You're all not all equal.
Yeah.
Some frameworks are better than others.
And since you have PowerPoint, it'll probably be okay. You just have to be careful not to. But then you can just go back up.
Yeah,
but this seems to be not too sensitive. Sometimes in PowerPoint, it's so sensitive it clicks to the next thing.
Probably good to use that.
That's what I'm going to be talking about. Because when it comes down to it, in the end, you have one estimate.
Yeah.
You can focus
on
on
screen is so sensitive that sometimes typing the keyboard is the same. That's the approach to cursor.
Yeah, you have all these different stages.
Yeah, and then it just goes to the end. Sometimes I do that. I hit the end instead, and it goes all the way.
Now, when you want to reduce the area,
all right. So, thank you. Sorry for all the weirdness. I was thinking, today's going to be easy because we don't have any remote people coming in and talking remotely. Thank goodness.
All these things, sharing applications.
Oh, yes. Oh, I want any kind of, I really test this out.
Yeah, we heard. Joe was saying from the last workshop that these errors kind of keep it. That's true. You have 5% here, 5% over here, and 5% of the process. I had to get my email. Put them all together. That could be, unless you mitigate, you can try to mitigate.
I was just here early, to get ready, and I was actually down here early.
Well, it's like I had Ragu and Bill emailed me their stuff, and I just never. Oh yeah, I'm getting on to I got it on my head. It's like.
I know that's it. I would have been all right.
would love it if I could shove a USB memory drive in this thing. Like, there's the preset.
I'm so sorry, Linda.
No worries. No worries. So what was the deal? It's always it was like a roller.
They could still look at changes.
Well, I knew there was, and I told him my problem. Working on the problem to ask him what the problem is, because they just slow things down. So I knew you were working on it as hard as you could. So that's how we did it.
Which I'm working with, starting at 11:18.
Okay, guys, let's get started.
How's that? And we're good here on the, okay, perfect. And we got the little mics here. Perfect.
All right. I'd like to thank everyone for showing up again. Our speaker for this session is Dr. Trevelor Ragnathan. Raghu, for short, has a PhD in statistics from Harvard University. He is currently a professor of biostatistics and director of the Survey Research Center, University of Michigan, and research professor at the Joint Program in Survey Methodology, University of Maryland. Dr. Raghu will present some ideas about issues to consider when combining information from disparate sources and the methods for assessing the sensitivity of inferences using imputation framework. Our discussant for this session is Dr. Bill Bell. Bill has a PhD in statistics from University of Wisconsin. He is currently the senior mathematical statistician for small area estimation at the U.S. Census Bureau. Bill has been at the Census Bureau since 1979, has been primarily working on time series modeling and census coverage estimation and small area estimation.
Thank you very much. And I'm delighted to be here. And Linda has told me that I think I might have a lot of questions on this work, and it's going to be very controversial. So I don't know. I think she must have seen the slides and then said that, oh, this is going to be controversial. So we'll see how it pans out. I'm delighted to be here. And then, so when looking through the program, I thought that maybe I can start off with a case study that I've been involved for the past quite a few years in bringing in the multiple data sources into a particular problem that we are trying to address. This is a joint work with David Cutler at Harvard, and then Susan Stewart and a bunch of other people. And I put a ... because I've had many students come and go during the past a few years that we have been working on, taking in different aspects of this problem and then developing methodologies as they go along. So last of the students is Paul Imbriano, who's going to go and work for FDA. So this is so this kind of a digital revolution is although very old. I remember, I think, in the graduate school days, I analyzed the data of wind speed that was measured every second. And these were all measured on a windmill in a various military bases, because that was the primary source for getting the power. And those wind speeds, if they exceed too much, then I think there was a burnout of the systems that stored the batteries. So they wanted to know whether they can predict the angle with which they should shift, so that they can predict what angle they should put it in, so that they can minimize the burnout. So I modeled a long time series of multiple windmills, and then of course they were going to put it on a simple computer there on the unit itself, so which will predict what the angle it should be, and therefore they can reduce the. So I had to take all this data every second, but then reduce it to some simple equation that they can program it into that unit, so that will predict what angle it should be, and therefore they can stop. So this is a long time ago that predictive modeling I've been doing. I think this is kind of now I think with more and more data becoming available, our computing sources are becoming available, and it's kind of a great opportunity it affords all of us really thinking about what kind of inference then we can draw by combining data from multiple data sources. At the same time, you're also facing this challenge in terms of the probability samples, declining response rates, and increasing cost. And as a director of the survey research center, not a day goes by when somebody knocks on my door. I'm saying that I am too expensive, and that's the way it is. So the costs are going up, and then you're not able to collect all the information needed because of fatigue or because of the limitations. So the leveraging of data from multiple data sources is going to be an important aspect for us, and then we need to think about the individual data sources and bringing them together. So there's a quality standards for each individual data sources, but there's also a process by which we integrate those data sources. There are quality aspects of those integration aspects itself. So I think that we need to think about the evaluations of whatever the estimates or whatever aspects we are bringing in, to think proactively in terms of how I'm going to evaluate these estimates. So in that context, I'm going to take one particular example of explaining the cost, the medical expenditure, medical spending, and then how it is related to these health conditions that people have, and then can I really dissect this cost changes over time into the changes in the cost of treating those conditions, as well as the changes in the prevalence of those conditions. So here is the graph. This is for the 65 and older. So the one on my left, and then gives you cost, average cost per person. These are all in 2010 dollars over the period of 1999 to 2012. You can see that the cost has gone up, but at the same time, you can also see that there is a slowdown of the cost for the 65 and older. So it's not exactly linear. If you predict a linear interpolation, you will get a much higher cost. But I think you're seeing the much slowdown in the medical spending. On the other hand, you can see the on my right, there is the average number of conditions, the health conditions. So we have about 107 health conditions that we have defined for people: hypertension, diabetes, and so on, AMI, and these are all defined based on the various ICD-9 codes. There are about 107 conditions, and then we are totaling how many conditions per person on the average they have. So they start off with something like 13.5 conditions in 1999. Now they are almost like close to 18 conditions in 2012. So the conditions are also increasing. The change in cost of treating these conditions, that new drugs are coming in, the expenditures are also changing of treating these costs. So we really want to dissect this, the changes in costs and changes in conditions, to really create a framework for understanding this dynamics of the cost changes. That was the whole idea of this particular project. And the three main objectives in this particular project was to estimate the prevalence rates and assess the trends for various diseases and screening rates. And then we want to estimate the costs that are attributable to each disease and assess the trends in these costs. So how much we are spending on hypertension, for example, or how much of this cost, total cost, could be attributed to hypertension or diabetes or AMI or any of those conditions. And then they dissect the change in total cost. So, and then we want to take the total cost changes that is happening, and then said what portion of that is happening because of changes in the prevalence rates, and what portion of that are happening because of changes in the cost of those treating those conditions. So that was the objective of this particular analysis. So we divided the population into 4 groups, 65 and older, and then 45 to 64, 18 to 44, and less than or equal to 17. So these are the 4 groups that we decided that we would be dividing in, because the dynamics are very different for chronic conditions. Some of the chronic conditions play a big role in 45 to 64. And then childhood health condition may play a big role in less than or equal to 17. So we decided that we will be. Another reason that we divided this population into these 4 groups, because the data sources available are quite different. And so we want to make sure that we are using the maximum number of data that are available in order to address the issues in these different populations. So looking at the landscape of what survey data that we could use is for the elderly, by far the best data is the MCBS, Medicare Current Beneficiary Survey. There's also Medical Expenditure Panel Survey, National Health Interview Survey, NHANES. We also have surveys, Health and Retirement Study, Panel Study of Income Dynamics, National Comorbidity Study. These are all different diseases. They're all covering the different aspects of those diseases. We also put together several non-survey data sources. These are Medicare claims. We have negotiated some access from the provider data, some of these HMOs, IMS, and some prescription prices. These are all also non-survey data we have assembled for a project. And then we also have information from various clinical studies. So we want to really assess whether or not the prevalence estimate that we are getting is really borne out by some of these clinical studies or not. I'll come back to that that issue of validation, quality, and so on that we use in this context. We identified about 120 diseases, screening conditions, but only 107 of them are for this elderly population, 65 and older. For example, pregnancy is not really valid for the 65 and older. So there are some diseases that are not valid for these diseases. So 120 diseases include a variety of conditions that cuts across all these population groups. So for this project, I'm going to mostly focus on 65 and older, and then we also had to do these analyses because the data availability is sometimes they are available only in restricted data centers, sometimes available publicly available. So we had to use mix of analysis. Some analysis are being done in the RDCs, some analysis are being done outside of RDCs. So this analysis where we are combining data from MCBS, Medicare claims, and NHANES, those are the 3 sources that we are using in this particular 65 and older. We can do it, but you get the data under the data use agreement from the MCBS, from the CMS. We are getting the data under some data use agreement. So, so the primary data source, age 65 and older, we now consider years 1999 to, initially we considered only 1999 to 2010. By the time we were done with 2010, 2011 and 12 became available, so we said, okay, now let us do 2011 and 12. Now, by the time we did the 2012, 2013 has become available, and the machines are running now for the 2013. And relief is that CMS has decided they're not going to use 2014 data. So I think we get a 1-year rest so that we can get ready for 2015. So we want to make this as a production aspect so that we are running this report on an ongoing basis. So as I said, 107 diseases and screening, and we decided that we want this to be a dummy variable. So 107 dummy variables that we want, because we just don't want prevalence rates, but we want to use them as outcome variables or use them as a covariates. So because they are the covariates for predicting the cost. So we decided that what the structure we need is the 107 dummy variables in the data set. So therefore, we can use it for multiple purposes. We also wanted to, for the 65 and older, we wanted to deal with the community dwelling subjects as well as institutionalized, like in nursing home, assisted living population, so on. Now, one immediate problem that we came up was that the people, the data set that we have full data on, or they were all on purely on Medicare. So if they were getting care from HMOs, they were not included in the database. So, and about 25%. Over time, I think there are about 25% of the enrollees are getting care through Medicare. So we don't have care through HMOs, so we don't have the data from them. So we did a simple propensity score weighting to compensate for those, for excluding those HMO enrollees, and we did as best we could in terms of trying to make sure that the model is good and there's an overlap of distribution of the propensity scores, and that way we can get the weighting done for the people. So therefore, this analysis focuses only on people who are purely covered on Medicare on 12-month basis, and they get an additional weight to compensate for those people who are getting care from HMOs. And then we also apply a multiplier to the cost so that the weighted estimated population total agrees with the published national health expenditure. So we want to make sure they're calibrated. So what our total cost exactly matches with the published national health expenditure produced by Census Bureau. So all these costs are in $2010. So we said, okay, now we need 107 dummy variables. So we said, well, there's one option is to use the Medicare claims. So that we can use the Medicare claims is that any claim indicating a particular ICD-9 code would define what that dummy variable would be. So we had a mapping of ICD-9 codes with those 107 disease categories, and we said, okay, now if the claim is that there is for that ICD-9 code, then that thing we said, well, that dummy variable is equal to 1. So the prevalence rate based on this definition seems reasonable for some chronic diseases, but very low rate for acute conditions. So remember, I'm looking for prevalence, that is, for a person ever having that disease, rather than whether they had the disease in that year of the survey. So for example, I will show you some examples. So if you look at the AMI or hip fracture, those are very underestimated in the claims because they would have the claim only if that happened during that year. And there's a low rate for acute conditions. So we decided that we need to correct for this potential underestimation of the disease dummies based on just a claim for some of these conditions. Otherwise, I think we'll get a very inaccurate picture of the prevalence rates as well as inaccurate picture of the attribution of the cost. So in this case, we decided to use sort of a self-report from the National Health and Nutrition Examination Survey as a way of calibrating this. So all these calibrated claims can be thought of as ever having a disease. So here is an example. This is for the 2001. So you can see that the hyperlipidemia, in this case, self-report in NHANES, if a doctor or other professional ever told you that you have a hyperlipidemia, about 44% are saying that, yes, I have a hyperlipidemia. But if you go and look at the claims, there was 36% of subjects have a claim for hyperlipidemia. And again, look at the hip fracture self-report in NHANES at 3.51, and then, but if you look at the claims, they're only 1.12% of hip fracture are captured there. In the middle column, there is a self-report for MCBS as well. So MCBS itself asks some questions about some of the self-report. So for this project, we decided that we will set aside all those self-report from MCBS so that we will pretend as though we don't have any of this self-report MCBS data. Because why? Because then after calibration of the claims and the NHANES, we want to compare it with the MCBS self-report. So we are taking the MCBS as sort of an external validation that we want to do for our combined estimates of the Medicare claim plus NHANES, whether or not that matches with the MCBS self-report. So if you use the MCBS self-report, then it is sort of cheating. So we want to pretend that we don't have any self-report from MCBS. So on the other hand, if you look at the diabetes, the self-report is 17.9%, and then self-report in MCBS are 18.9%, and then claims-based MCBS is 18.6%. That pretty much lines up on the diabetes. Because ICD-9 codes, the people write if you're going for the diabetes, they write, so that is captured in a routine care visit. So if you look at the hypertension, again, if you look at this, a little bit of underestimation in the claims-based definition of MCBS. That's because I think these people have multiple conditions, and the rooms for writing how many ICD-9 codes they can write, they may be limited. Therefore, they are not capturing the hypertension. And therefore, it's kind of down the line, and there are lots of other conditions, and they're taking priorities, and also they are more expensive to treat. So they are indicated in the claims. Now we have a bunch of conditions for which we don't have any kind of a calibration data, like thyroid disorders. So we have 13.9. That's the only thing we have with the claim. So 4.69 for depression for this particular population. We can try to get that from HRS, Health and Retirement Study. We can try to get that depression. That's what we are trying to now bring in the Health and Retirement Study as well to fit in some of these self-report data. Dermatologic diseases, we don't have any survey that asks the question about dermatologic diseases and so on. So we are going to have a mix of cases where prevalences, where we have data in the claims for all of them, but we don't have a self-report data on all of them. So we really have to do some modeling framework to bring about the corrections for those conditions for which we don't have any here is the scatter plot of a self-report and claim-based prevalence rate for the 2005 and 2012. So you can see that all those lines below the 45-degree line are the ones that are going to be calibrated. They're going to be moved up because they're all underestimated. And the lines above the 45-degree line, the claim-based rate is already higher than the self-report rate. And as we'll come back to that, I think how you treat that sort of overestimation, the claim-based rate compared to self-report. So the way I think we are dealing with this is that we have a MCBS data that have a bunch of covariates, and you have a claim-based definition of the dummy variables. So you have a claim equal to 1. This is a kind of a schematic display of one disease, one of the dummy variables. So you have a covariate, and you have a claim as 1, 0 variable. That you get from the MCBS. And in NHANES, we have a same bunch of covariates that are common covariates between MCBS and NHANES, and then you have a self-report variable 1 or 0. So these two data sets are going to be brought together, one below the other, by appending the data one below the other, by defining that if a claim is 1, then I'm going to say that person has that disease. So I'm not changing the claim. Claim is 1, that means they have the disease. If a claim is 0, then I don't know whether they have the disease. Right? The claim is, if the 0 means they may or may not have the disease. Then the self-report equal to 1, self-report equal to 0 is pretty much from the NHANES. So the whole idea now is to you treat this as sort of a missing data problem, and then impute those missing values. And then one thing that we are doing is that after imputation, the rates from the calibrated, we call it the calibrated claim, that is after imputation, the claim we're calling as a calibrated claim. After imputation, the calibrated claim should match up with the self-report. So that's what enhanced rate and then imputed MCBS rate should be similar. And they should be, they won't be exactly the same because there's a sampling error, but they should be as close as possible. That's what the condition we are imposing in the imputation process. And this is what we are doing for all 107 health conditions where we are calibrating them to the self-report as much as possible. Now, as I said, this you can do for the conditions for which we have a self-report data in NHANES. So what about those conditions for which there is no self-report? So there we are taking this as a measurement error model approach. So we have a calibrated, uncalibrated rates for those for which we have the self-report data. And we are taking that measurement error model we are building between the calibrated and uncalibrated rate and applying that to all the data for which we don't have a self-report. So basically I'm modeling the relationship between calibration and uncalibrated and then transporting that model to all the cases for which we don't have a self-report data. So it's kind of a measurement error model. So it's kind of a calibration is carried out for each year separately for community and institutionalized population. And we did it separately because one thing is that because we are going to estimate the trends, we didn't want to impose any trend in the imputation process itself. So we did it stratified each time or each year. And then we also, because the institutionalized and non-institutionalized population could be quite different, we did it separately as stratified. So we created 5 imputed data set with the calibrated claims, And there were some few missing values in the other covariates. They were also imputed. Then you obtain the prevalence rate for each disease and year, and then you perform a trend analysis using hierarchical model or whatever analysis that you want to do to look at the trends. And in this process, we performed sort of because we are integrating all these different models, so we had to perform lots of model diagnostics, imputation diagnostics to make sure that the things that we are doing are reasonable and sensible in this context. So here is the data from NHANES 2009-10 and MCBS. Now you can see that the diabetes rate is 23.72% from the self-report, and MCBS is 23.9, but claims was higher in this year. So 2009, there were a lot more claims for diabetes. So because we made the decision that the claim is truth, if they have a claim, they have diabetes. Therefore, so we didn't have to do any changes because it's already higher than the NHANES rate. So the calibrated claims remains the same because we didn't do any calibration for them. And one interesting thing is that in NHANES, especially, they ask the question whether they have a diabetes or not, but they also measure their A1C level in the lab and fasting glucose for some people. So we could get an idea of undiagnosed diabetes. So, for example, if suppose somebody said no, that doctor never told me that I have a diabetes, but then they were in the measurement lab side and they said that yes, they have a higher HbA1c and or fasting glucose. That means they have a diabetes actually, but they don't know it. So that's what I call it, undiagnosed diabetes. And we could consider that as a condition for which there is no claim, but you can try to impute what would have been in the calibrated claim for the MCBS. So we are imputing that in the MCBS. So again, hyperlipidemia, which was very low in previous years, suddenly became big thing in ICD-9 code capturing. So you can see that MCBS now captures almost 61% of claims are capturing that. But that's uneven because some of the older populations they don't exactly get that claims. So there's a slight increase in calibrated claims because of the unevenness. Similarly, you can look at the hypertension is also more and more claims are being captured. One thing I wanted to bring it out is the acute myocardial infarction. So in the self-report, 8.58% of the self-report in NHANES say that yes, we have I have had AMI or heart attack ever. But in the MCBS claim, only 2.3%, but our calibrated claim raises it to 11.19%. So you can see that I think all these are moving in the direction of correcting it. Underestimation are corrected, but the overestimation are left because that's by design. We didn't want to change the claims data. So here is the same graph now for the calibrated claims versus the self-report. You can see that most of them now are calibrated right close to the 45-degree line, and that's what our intent was, to make the claims, bring it back to closer to the self-report. So kind of achieve the goals that we wanted to pursue. So we also look at the scatter plot of the trend estimates from the self-report versus the claim-based versus the calibrated claim-based. Now, if you look at the claim-based compared to the NHANES, it's almost like a flat line. There's almost like a claims, there's no change. Whereas if you look at the calibrated claim, it's capturing the changes. So that's what we wanted to see, is that whether the changes in the calibrated claims trend estimate are closer to the trend estimate from self-report, and that it seems to be doing in that context. After this, we also assembled a room full of all physicians and gave them all these estimates of blinded estimates, the calibrated claim estimates, and then calibrated claim estimates. And then they had to rate which one they think is the closest to their experience. But it's not a great, but just something judgmental. So they were blinded, and then they were given the sheet, and then they had to write which one is close. And then some trick we did also is that within the row we have a diseases, and we have a calibrated claim, and then we have the claim, and we didn't want to be all same claim, calibrated claim, so we kind of randomized the shift. So columns were randomized, rows also were randomized, and then they were distributed, and then they marked. And almost all the cases, calibrated claim came out to be the winner in the sense that they all thought that calibrated claim was giving reasonable estimate. That's not a proof, but that's another assessment of how well we are doing. Now the next thing is, okay, now we have this 170 dummy variables. Now how are we going to attribute the cost for those conditions, 107 conditions? So here we took a sort of a cause and inference framework where you have DJ is a disease under question, so for example hypertension, and D minus J is all other diseases, so 106 of those dummy variables. And then X is a covariate and Y is a total cost or spending. So here the attributed cost for the disease was defined as a difference between the average cost for the person with the disease versus the average cost for the person without the disease, all other things. So that's the way we defined the AJ to be the attributable cost for that particular disease. Now, of course, this is naive because this doesn't really take into consideration when you go package deals. So when you go with the 5 diseases, it's not cost of each of those diseases. You get a economy of savings. If you more conditions you go with, you get a lesser discount. So so in this case, for estimating this, we kind of created a propensity score classes for the diseases, and we created the strata, and then the mean difference in the cost for those with and without the disease, and then you take the weighted average of these differences weighted by the population size in those. So then we computed attributable cost for now 80 diseases, because some of the diseases were so low prevalent we couldn't really do attribution on a yearly basis. That's what to do when your prevalence rates are pretty low. So for about 80 out of these 107 diseases, we were able to do it for each year. Now it is 14 years, 1999 to 2012. So then it said, okay, now how good these cost estimates are. So we said, well, let us add up the cost, what we have attributed, cost for the diseases, and then if the person has a disease, then we attribute the cost. So we get this aggregated cost. So you can add up all the dummy variables the person has, associated cost, and that's the total cost. That's aggregated cost. So we said, okay, now how comparable are the aggregated costs that we got by adding the individual costs with the actual costs that they reported or they derived from various sources? But of course, the costs will depend upon many other things like number of hospital stays and conditions. That is, as I said, about the economy of scale, when you go with multiple conditions, and whether or not that person died in that year, because that's the biggest factor, is that death during the year is a big component of the cost, and that's almost kind of like on the average $135,000 during that year of death. So we kind of looked at some sort of a adjustment model for these other factors. So we came up with this 8 covariates. So the number of health conditions squared, because it's economy of scale, and dummy variables for inpatient days, number of inpatient stays, and so on and so forth. And I'm running out of time. So we estimated the adjusted cost, and then we said we compared the adjusted cost with the actual cost. The one in the red is the kernel density estimate of the adjusted total cost, and the one in the black is actual cost. This is for 2009 and 1999. They're pretty much nicely overlapping between those two costs. So this attributable cost and then the 6 covariates are essentially building block for predicting the actual cost. So next, I think we wanted to really, again, I'm going to skip this one. The next one was this what if scenarios. So here's what is called, we call it as a causal matrix. So suppose, say, we fix the prevalence to be 1999. So nobody is allowed to get more after 1999. But only cost is supposed to change. That is my first row, 1999 row. That is, if you hold the prevalence same, but allow the cost to change, what would have been the actual cost? So 13,103 is the actual cost, mean cost per person. But if you fix the prevalence at 1999, but only allow the cost to change, 13,560 would have been the average cost. So that difference is attributable only to the change in cost from 99 to 2000. And everything, prevalence is as constant. Same way as a column is that you fix the cost but allow the prevalence to change. So 13,405 is the cost that would have incurred if you allow the prevalence to change but hold the cost constant. So that's what we call it as a kind of a counterfactual of the prevalence versus the disease. So it's kind of hard to look at this picture. So here is a smaller cost here and prevalence here is given here. So you can see that due to prevalence, the change is about $83. So there are $370 per year per person change. That's what we are seeing in the diagonal elements here, and that we can break it down into $83 is because of the prevalence changes, and $287 is because of the cost changes. So of the 2.3% change annually per person, 1.8% is attributable to the cost, changing cost, and then only 0.5% is attributable to the changing prevalence rate. So that's the kind of analysis. Now we are in the process of doing the analysis for the spending down and so on. These are now we also did the analysis for the 7 broad categories of diseases like cancer and so on. Again, the change in the cost is a lot more for the prevalence, is a lot more because of the cost, but not because of the prevalence. So similarly, we had done for 28 categories, 38 categories, so as many categories as possible. Now we had to validate these cost changes, so we are going back to those HMOs and then trying to get the data on how much actually they change the cost on the I think there are a lot of issues that we had to deal with, and then I'm going to close with this and saying that one is that the face-to-face interview of the respondents reporting the health conditions versus the physician reporting about the patient based on the medical records. So they could be very different because an interviewer asking the question could be quite different than the physician reporting it. The differing modes of data collection, the surveys that we are putting together, some of them are mail, some of them are telephone, some of them are face-to-face, or some of them are mixed. So we have to really be careful about whether there are any mode effects that comes into the play. Now, the response error properties might differ in the two surveys. So a survey may be conducted by a well-known federal agency and also or by a reputed institution, but not that well-known. So that could also play a role in this response error property. The differences in the survey design. So, for example, HIS is a face-to-face survey design, but NHANES also involves a face-to-face survey as well as measurement lab. So the respondents recalling activities could differ by the two survey designs. So if I know that I'm going to be called into the lab and taken the blood out, and whether that thought will make my recall properties about my diseases more accurate, then I know that nobody's going to call me out by drawing the blood. So I don't know whether that plays any role in this kind of a calibration. The differences in the question wording or the placement of the questions with the same wording may provide different stimuli to respondents and different error properties. So we have to deal with these, where it is placed, where these health conditions are placed, in what context it is placed, to see whether or not the dummy variables constructed from one will be comparable with the dummy variables constructed from the other. And then combining a survey data and administrative data source has a differences because in a survey, every respondent receives the same stimuli. So everybody's asking the same question. So therefore, that is a constant stimuli being given. Whereas in the administrative data source, I don't know why doctor puts hypertension first or decides to omit hypertension. So we don't know. Every hospital system could be quite different in terms of what order they are suggested, what order they have to be put. So we don't know whether. In this example, also we considered that if a person has a claim for that disease, that means that person has a disease. Now, one could question that. Is that really a valid assumption in this? But in this case, we did not want to change the administrative data. Therefore, we just used that to be the sort of a if they have it, we have it. So, in conclusion, with these challenges, the combining data from a mix of probability and non-probability sources kind of provides an exciting opportunity. And in this world of big data, where everybody's doing big data, because we have done big data a long time ago, but somehow I think they have forgotten that we have done the big data. I remember in University of Michigan, we used to process the entire state unemployment data. We used to get that entire state unemployment data, and we used to process that. That is huge data, not a big data, but huge data. So, and again, in terms of the representativeness, measurement error, you have to really think through these issues. And in the end, I think I would say that it's dangerous to think that we don't need a high-quality probability surveys anymore. That's the danger that we are in, saying that everybody says that, I can do all those things with a fraction of the cost. But if you remember that in almost all validation, they go back to the probability survey to calibrate or to look through. And if we didn't have any of those probability surveys, we will be totally at loss whether what number we are getting is that right valid or not valid. So I think we may want to be smarter, but not totally abandon the probability surveys. Thank you very much. Sorry, I ran over.
I'm going to start by making some general remarks about small area estimation and how it works at combining multiple data sources. Then make an attempt to relate that to Raghu's project and look for key elements that I think generally are in common. And then I'm going to make some remarks about what one looks for in terms of quality of an effort from small area estimation. There. Okay, so here's my two-slide overview of small area estimation, done in the context of the most fundamental small area model, the Fay-Harriott model. So we have some direct survey with little y. Oops, it is too sensitive. That are estimating some population target, capital Y, with sampling error E, I, for area I. And then the population target is given a model, here a linear regression model with some covariates X and an intercept and random error that also is called model error, the random effects, and regression parameters, etc. And so given a specification of a model like this, we fit the model, and the favorite approaches seem to be either restricted maximum likelihood or a Bayesian treatment. And a way to think about what's going on with model fitting is that effectively this calibrates the covariates we have, the X's, so that the regression function here is predicting what we want, which is this population target, which is also what the survey estimate is estimating. So by fitting the model to the survey data, you allow for the sampling error, you get regression predictions of the population target. And then we put the two together with a process called best linear unbiased prediction, which is given values for the variances here. These are the sampling error variances, and this is the estimated model error variance. We get this weighted average of the direct survey estimate, little y, and the regression fit. And here's the formulas for the weights, and it's maybe not immediately obvious. These turn out to be inversely proportional to the respective variances, the sampling variance on the one hand and the model error variance on the other, so that, for example, when the sampling variance gets really high, because the sample is very small for an area, the weight on the direct survey estimate goes down, and almost all the weight is put on the regression fit. And if the sample is very large, the sampling variance goes down, and almost all the weight gets put on the direct survey estimate. So that's small area estimation in a nutshell, and you can have fancier models, nonlinear models, but the general principles are sort of the same. So what's needed to make this work? Well, first, we have to define what our population characteristic of interest is, capital Y, which I call the target. And then we need an unbiased, quote, survey estimate, little y, of the target. Now, in reality, the process is typically reversed. We have a survey that produces estimates, and the target is implicitly what the survey estimates are estimating. trying that, but survey estimates are never going to be 100% accurate, even on the concept. There's non-sampling errors leading to biases. But typically the target is implicitly defined as what the survey estimate is estimating. Now we also need, I'd like to mention, decent estimates of the sampling error variances in this. And I just want to make the point that if you have very poor estimates of sampling variances, which is what you would expect when your samples are small, then that can affect the process, and you need to do something about that. And then we need covariates that have some relation to the thing we're interested in predicting, and we need that, the important point is we need that relation to be consistent across areas, across observations. If it's inconsistent, that can lead to problems. So note that these covariates don't actually have to themselves estimate what we're interested in, because the model fitting calibrates them to predict what we want, but they do have to have a consistent relation. One other point that I'll briefly make is if we want to pull in another survey estimate, or even more than one other survey estimate, it's not generally correct to just stick it in as a regression covariate. The better way to do it is the bivariate, or more generally a multivariate model. And so we write down the equation twice, and then I don't want to say too much about this, but we fit this jointly, and we recognize there are two targets, even if the survey estimates are ostensibly estimating, quote, the same thing, like two poverty estimates. You don't want to make generally the assumption that those targets are exactly the same. So we allow, we allow the targets to be different. Recognize that, because even if the two different surveys are trying to estimate ostensibly the same thing, they won't perfectly achieve it generally. Okay, so what does all this have to do, or have in common with what Raghu was talking about on his project? So I tried to, in looking at his slides, figure out how I could make connections. So the first point is we need a data source that effectively defines the estimation target, capital Y. And in small area estimation, as I said, that's generally the survey estimates you're starting with. In Raghu's project, it looked to me like it was either the N. Haynes data, or I think now I have this right, it's a combination of the N. Haynes and the Medicare claims data. So that's defining a truth that he's trying to shoot at for prevalence. Then we need covariates with a consistent relation to the target. And I'll mention, for example, in our small area income and poverty estimates project, we have covariates obtained by tabulations of tax data and SNAP participants data. Raghu has various other data sources he mentioned. The claims data, I guess, is maybe, I don't know whether to call that a covariate or it's just used for the target. And then the model fitting and prediction calibrates these other data sources to predict what we're interested in. And in Raghu's project, the prediction seems to involve this imputation, which is a little different than classic small area estimation. And I think these general elements are the key elements that would come about in any attempt to combine multiple sources of data. And they can show up in somewhat different forms. So what problems can arise for this approach? Well, one problem that one could have would be you have a target and population target in mind, and maybe candidate survey estimates, but none of them seem suitable for actually precisely defining the target. So that's like all your data sources are substantially biased with respect to the target you're after. And I mention this only because every once in a while I see something where somebody has a project where they're concerned about biases in their estimates, and they seem to have in mind that fitting a small area model will address this, and it won't. Because small area estimation is about reducing variances, not about getting rid of biases. You need other data to bring in to address biases. Another problem is if the relation between the target and covariates is not consistent across areas or observations. And why might this happen? Well, you can suspect that if you know something about the quality of your covariates that leads you to believe that they're not consistently defined or consistently measured. And an extreme case of this is where the covariate isn't even available for some areas. So that leads to problems. I'll mention a couple examples from the SAPI project. At its inception, one data source that was considered was free and reduced price lunch data, which had certain advantages because it was a data source defined for school districts, which is the ultimate geographic target that SAPI has. But it was also known that the way the data were collected was different area to area, even within states. It really depended on how the program was administered. And after some assessments, it was judged that it was too inconsistent to be used. Another one that came up was with welfare reform. It affected the nature of the SNAP data, formerly known as food stamps. And what happened was, this is key statistics on the regression coefficient on our SNAP participants data. And for 3 age groups that we model. And in the middle part here, this is between 96 and 97 when welfare reform went into effect. And that changed how the program was administered. And what happened was for all 3 age groups here, the key statistics went insignificant for the most part. And over time, the program stabilized, it came back, and we ultimately put the variable back in the model. But I don't know, do I have a few minutes still? I want to make a few brief remarks. As I was sitting here, I got to thinking, I hadn't really said enough to kind of relate to the issue of output data quality. So I wanted to make a few remarks that come out of small area estimation in regard to this. The first one is, and I don't have this on the slides, unfortunately, but it's not technical, so and I don't have any formulas or anything. The first I mentioned is that the goal in small area estimation is variance reduction. So you got these survey estimates based on too small samples. The variances are too large. You model to reduce the variances. So that makes it clear that the way you would want to judge this is by judging how much variance reduction you get. And when you do this with formal models, you get that because the give you prediction error variances, or labeled as mean squared error. These are optimistic because they believe that the model is true. So when you take that into account and then ask the question, okay, am I getting enough improvement here, given the concern with using a model is what happens if the model fails? You want to look for a substantial improvement. How much is that? Well, I thought, I attend various small area estimation conferences, and I thought John Rao, who's written the book on small area estimation, was one of these, had said you look for like a 20 or 25% reduction in variance at least. And I mentioned it to John another time, and he couldn't remember that, so I'm not sure. But I think it's not a bad, you want some threshold like that. You don't want to get 10% improvement from a somewhat complicated model. That's not enough to risk problems if there's a problem with the model. But a lot of times in small area, you can get huge reduction, 50%, 75%, and also the case where you have areas with no sample, where you produce estimates where you had none before. So there's an easy sort of quality standard to look at, is how much variance improvement do you get. The second point, which I mentioned, is that small area estimation doesn't address biases in your fundamental survey data source, the one that you want to use to define the target. Let's see, what was I going to say? But but if when you're pulling multiple data sources together, it is addressing biases and other ones that are covariates through the model fitting. And one final point is that in some cases there is an external data source that can be taken as something like a standard with qualifications, I would say, that one can use to assess quality of small area estimates. Now, if you do that, you're making some assumptions about the quality of this external source being used as a standard. And if you just use it without sort of any adjustments, you're implicitly assuming that any differences in relative biases of the standard compared to what the data is you were using to produce the small area estimates is negligible. And that may be true, it may not be true, but it's worth some thought. And to just cite an example, this came up for SAPI with respect to evaluating school district estimates, because for school district estimates, we had an estimation procedure. We didn't have a formal model. So it was harder to judge statistical uncertainty there. But what we were able to do is produce the school district estimates from our estimation procedure for years corresponding to the 1990 census and later the 2000 census. So there were long-form estimates that could be compared against. Now, the long-form estimates were not themselves taken to be perfect. At the school district level, many of them have substantial sampling error, but that can be allowed for in comparison. So we had the long-form estimate minus the estimate from our procedure. We were able to produce estimates, infer estimates of prediction error variance for the procedure that we had for the school district estimates, and get some handle on the magnitude of the error in those estimates. Again, you do that when you have more concerns about things like sampling error and variance than you do about differences in relative biases. But anyway, another way to evaluate estimates is to have some kind of standard like that to compare to that's at least good enough for that purpose. And if that's from something like a large sample, you want to allow for sampling error in doing that. Thank you.
Thank you, Raghu and Bill. We have about 5 minutes for questions, and we'll have maybe an hour for lunch. Any questions? Yeah, please come up, say your name, where you're from.
Hello, Stephanie Ekman from RTI International. I just wanted to comment on a comment that Raghu had made about the differences in response behavior when people know you're going to be checking up on them. You ask them if they have diabetes, but they know that you're also going to test whether they have it, and so does that change the way they respond? And I did a paper on that in a different context with a student in Germany looking at administrative data. We put forth two hypotheses, right? If you know somebody's going to check your answer with the administrative data, you could be more accurate because you want them to be, like, proud of you. Or you could be less accurate because you know they're going to throw away what you say anyways, right, and get the right answer. And so we looked at that for just a few variables, and we found more evidence on the worst respondent hypothesis. It seems to make you a worse reporter in the economic context about unemployment measures. I'd love to see that or hear about other people who have done it in other contexts like the health one that Raghu mentioned. Thanks.
Hi, I'm Chris Chapman from NCES. So we're good. Quick question for you, which is never going to have a quick answer, but you mentioned that you took your data from the different sources and you constructed dummy variables so you can make them applicable across sources and you can mix the data together more easily. I'm wondering at a couple different levels, if you've done some kind of analysis to see what happens with the pure underlying data in situations where you didn't have to turn them into dummies, were there some ways you could evaluate the effect of your modeling in your imputation approach that would give people like myself consuming the data some sense of how much the modeling effect is having on the results, and how sensitive the models are to changing the components of the models?
Thank you. I think the reason that we chose these dummy variables is because we wanted to do lots and lots of analyses using them as predictors or as outcome variables. So in this context, we also did prevalence rate estimates just using a single data source. Suppose if we had NHANES, and then we said, okay, now we were going to do a modeling of the NHANES, just a self-report estimates. We also did a modeling of estimates that we can derive from the lab alone, and we also then did a modeling of just the individual component of claims alone. And so I showed some of the pictures there. I think is that using the claim alone, we got a very flat rate in terms of the trend estimates. So although there's no trend in the prevalence rates, but whereas when we use the enhanced, we got a trend estimates, and that's what we are trying to mimic in our calibration process. So the trend estimates using exactly the same hierarchical model approach, using the calibrated dummy variables, gave us the same answer as the self-report dummy variables in enhanced, and also self-report dummy variables in MCBS. Because remember, the MCBS for us is a standard to which we are comparing, because those are the variables that were not used at the outset. We pretended that we did not have those variables, and so we did different approaches to make sure that what we are getting is reasonable. But we want to express